Всем видно, да? И слышно меня?
Yes.
All right, let's start. Let me make a very short reminder on the short exact sequence, which is called exponential sequence. When we write a short exact sequence, which I wrote last time, the question is, this is a sequence of what? A convenient language is saying that it is a sequence of sheaves, but we don't use this term. Therefore, we can understand it. It is called, by the way, exponential sequence. Let us understand it as follows. That for any open subset in our manifold X, we have a sequence of sections. Okay, let U be open and connected. We have a sequence of sections. The sections of this object are just constants, constant integral numbers. So here I write just Z. Then we have sections of the trivial bundle O, which are just holomorphic functions. And sections of this O star, which are non-zero, non-vanishing holomorphic functions. So yeah, and of course we have maps, exponential map here, inclusion of constants, constant integrals into functions. For general U, the sequence does not have to be exact, but for small U, it is exact. And this is the meaning of the short exact sequence, if you wish. So this is exact for small U. for example, a disk. And this produces exact sequence of Czech complexes.
And here, when you say about sections, you say about smooth sections, yes?
Holomorphic.
Holomorphic, okay.
Complex, Czech complex for a good covering. And hence, long exact sequence in cohomology. Which reads as follows. It splits, as I said, into two pieces. The first piece is trivial. These correspond to H naught groups of the corresponding Czech complexes. And then and these are, in general, non-trivial. And this is the same as Picard group. Is it clear the last how to say sentence? And some terms after that, which you must know already. Okay. So I wanted just to make this origin of this long exact sequence to make it clearer. Okay. Now, let us make such a subsection, examples of computing cohomology. This will be this subsection will be very basic. So, but nevertheless, these examples are sometimes useful in practice also, but they actually do not give general understanding how to compute cohomology, because it sometimes can be a difficult task. Wait, let me add to the reminder. Let me add again, if we have a short exact sequence of just of holomorphic vector bundles, say I need for other means. This letter is S. Is a short exact sequence of holomorphic vector bundles which can be understood in two ways. Unlike the exponential sequence, where two participants are not vector bundles, but when all three participants are vector bundles, then this can be understood in two ways. So it is a sequence of morphisms of bundles. So the errors are morphisms of bundles. So fiber-wise linear maps. Of morphisms, vector bundles, holomorphic vector bundles, of course. And at each point of the base, we have exact sequence of fibers. Or we can understand it equivalently as above. That for any open U in X, if it is sufficiently small, the sequence of sections is exact. And again, sequence of Čech complexes. From this, we get sequence of Čech complexes. And a sequence in cohomology, long exact sequence in cohomology.
And in A, sequence is also exact, where you say about X.
Yes, short exact sequence.
In A also, okay.
Sequence of morphisms, is exact. Okay. Now, examples. The examples will reduce to the case of X equal to CP1. And let us consider only line bundles. Any line bundle in this case is isomorphic to so-called O of K. which I will describe now. Let us cover CP1 with two open subsets. With coordinates z and u equal to z to the minus first on the intersection. Then the transition functions for all of k are powers of z, namely, more precisely, a section of O of k is a pair of functions in this trivialization atlas. Say f naught f infinity, where f naught is a holomorphic function, a regular holomorphic function on u naught, f infinity on u infinity, and on the intersection, f infinity equals z to the minus k f naught. Now let us check what the zeros cohomology of O of k. Which is the same as global sections, I remind you. We simply have to check whether there exist and how many such pairs f naught, f infinity satisfying this junction property. It's obvious that it is like this. Okay, let us separate the case of positive k and negative k. So for k greater or equal to 0, it is a space of such pairs where f naught is a polynomial of degree at most k, and f infinity of u, I write it in the coordinate u, because then I will understand whether it's regular at u equal to 0 or not. It is u to the power k f naught of u to the minus first. Now it is clear if y f naught has to be such a polynomial, because otherwise f infinity would not be regular, right? So we see that the dimension of the space of global sections is k plus 1. Actually, I add here, it is true for k greater than or equal than -1. So for k negative, the space is, of global sections is trivial, is 0. Because in this formula, if k is positive, if minus k is positive, then multiplying any regular function f naught with positive power upset, we would get something which grows at infinity, and therefore f infinity wouldn't be regular for u equal to 0, right? Now let us see what are the first cohomology of these bundles. Okay, again, let us start with k greater than 0, greater or equal to 0. Now h1 are, what is h1 in Czech cohomology? It is a section of the bundle on the intersection, modular additions coming from two charts. So it's the space, it's the portion space. First I write, say, phi, which is a section on the intersection of charts of O of k. Modular equivalence phi is equivalent to phi plus f naught plus f infinity or minus. Let me write better minus, I guess. It's somewhat, of course, you understand it's doesn't make any difference, but still. Where f naught is a section on u naught, and f infinity on u infinity. These are not functions, these are sections of the bundle. Unlike my notation above, this f were functions, and here they are sections. Okay, let us, not to confuse, put hat over all the objects which are sections of some bundle, not just functions. Now, in our pair of local trivializations of the bundle, we have two trivializations, right? On two open charts. Therefore, I write plural here, right? F naught, say everything. F naught is represented by a function. I write it, say, F infinity is represented by a function F infinity. And what about phi hat here? Phi hat is also represented by a function, but for phi hat, we can use two trivializations because it is on the intersection, right? Let phi hat be represented as phi in local trivialization coming from U naught, all right? Then the equivalence relation here. This was a relation between sections. It will read as phi, the function representing the section, the cocycle, the section phi hat, phi plus F naught. But for phi F infinity, we have first to change trivialization. Therefore, it becomes to bring it to the trivialization of U naught. Okay. Now let us compute how many are such things. Functions phi on the intersection modulo such a relation. Equivalence relation, I mean. So phi as a function on the sphere without two poles can be written as a Laurent sum from minus infinity to plus infinity. F naught as a sum of positive powers of Z. And F infinity, it is a regular function of U, which is Z to the minus first. Therefore, it is a sum, say it's Z prime N, Z to the minus N, where N runs from 0 to infinity. Okay. What do we see now? We see, actually what we are doing here was for any k. So I erase here for k greater than 0, because we are doing this for any k. Now we split for k greater than 0 and less than 0. So okay, actually greater or equal to -1. This is a critical distinction. Okay, for simplicity, let it be 0. For k greater or equal to 0, what do we see? We see that we see that any phi is equivalent to 0, because f naught can be used to eliminate the positive part of phi, and f infinity has any powers, any negative powers. When we multiply with z to the k for positive k, some of terms here become positive power, but this was already accounted for in the first in phi naught. So phi f infinity still can have any negative. After multiplied with z to the k, this guy has any negative powers. I will erase this because I want to keep this formula for any k, but for positive k, this guy contains any negative powers. F naught contains any positive power. Therefore, phi can be eliminated with such additions. In other words, any one cocycle is equivalent to 0, and hence H1 on CP1 of O of k equals 0 for positive k. All right, let me now erase. Now for a negative k, F naught still eliminates in phi, can eliminate any positive powers, but this guy is now more restricted. For negative k, it always starts, it's, how to say, it's lowest order term in the inverse of z. Its lowest order term is z to the minus k, right? Therefore, what we can say that any phi is homological or cohomological, better to say, to such a Laurent polynomial. From n equal to 1 to n equal to, let me denote k by minus l, to n equal to l minus 1. All the powers starting from L can be eliminated by this term. Therefore, what we get, and the remaining terms which I wrote here cannot be absorbed into trivial cocycle. By trivial, I mean this part. Therefore, we have that the dimension of H1 of O of minus L equals to L minus 1. We shall check if I did not make a mistake here. Now let us recall the Serre duality theorem. It's a general theorem for projective manifolds. It relates, it's a complex analytic analog or algebraic, if you want, analog of Poincare duality, actually. It relates the cohomology HP, say X, let X be projective. In general, it holds for compact Kähler manifolds, projective complex manifold. And E holomorphic vector bundle. So sorry. Let me just this cohomology of the holomorphic vector bundle with its dual with H minus, so the dimension of X, complex dimension, let be n minus P of X E dual tensor Kx. I explain this, and we have the duality of these two vector spaces, where Kx called a canonical, the canonical bundle of X, and by definition, it is the top exterior power of the cotangent bundle. So the in the case of CP1, Kx Kx is isomorphic to O of minus 2. If you want, it is an exercise. Therefore, the third duality CP1 looks like this, that HP CP1 O of K is dual to H1 minus P. 1 is the dimension of the manifold, CP1 in our case, CP1. Now we have to consider this tensor product.
Sorry, but in definition of K, is T holomorphic cotangent bundle?
Of course, everything is holomorphic.
So this is T 0, 1 or how? Or 1, 0?
1, 0.
Okay.
And this comes from O of K dual tensor K CP1. And now if I denote the dimension of the cohomology group by lowercase h, then what we have HP for all of K, I use a shortened notation, is K plus 1 for K greater or equal to -1. And on the right-hand side, what we see, H0. And H1 of O 2 minus K, according, let us check our formula here, this one. It would be K minus 2. Wait. Sorry. I beg your pardon. It's a mistake. I wrote correctly that Kx is O of -2. Then when I multiply, I should have -2 here, right? Not +2. Agree? So let me correct. Let me write it like this: minus K minus 2. You see that they have the same dimension. So the duality, I mean, this is a check of subduality, so to say, or vice versa, check of our computations. All right, but now let us see how the third duality is realized by what is the pairing between cohomology space here and cohomology space here. The duality means there is an undegenerate pairing, right? Let us call it third pairing. General X, I mean projective or compact Keller complex manifold. How can we describe? We should pair HP XE and HN minus P x e star tensor kx. Any cohomology class here we can represent using the Dalbo cohomology. It will be represented by a differential form omega, which will be a 0p form on X with coefficients in E, which is d-bar closed. Modular exact ones, right? This should be in parentheses. The rectangular brackets denote this cohomology class modular exact forms, okay? And the cohomology class here is represented by, say, differential form mu, which should be zero n minus p form with coefficient in this bundle. But now recall that the canonical bundle is the bundle of top degree holomorphic forms.
Sorry, but by d-bar you mean nabla bar, yes? No, not just Dalbo difference.
Yes, nabla bar. Yes, thank you. Thank you very much. Yes, nabla bar. Where nabla bar is d-bar connection for E. But this is the same as saying that mu is a n comma n minus p form on X with coefficients in E star, which is again nabla bar closed, where a nabla bar is for E star. Now we can take the wedge product omega times mu and take its trace, and this guy will be now top degree form n comma n on X, and since we took the trace, it is just the scalar form.
What do you mean by trace?
The pairing between E here and E star here.
So this is not
So
trace, but just
omega, let's say, is a vector valued form, and mu is a co-vector valued form.
Mm-hmm. So there is no matrix here. It's just
omega times mu is a matrix. Okay.
I understand. Of rank 1.
Okay. I better write not the trace, but let us write in this way. Where is the pairing of E and E star? Okay, now the integral over X of this guy, omega wedge mu paired, is defines the pairing the third pairing. To understand that it is a pairing in cohomology spaces, these ones, we have to understand that the result of the integration does not depend on the representative omega in one class and mu in the other class. If we change with those forms with by an exact form, then the integral wouldn't change. Okay, let me write. This does not depend on representatives. If we replace omega by omega plus nabla bar alpha for appropriate alpha, then omega wedge mu paired with will replace with d bar of alpha wedge mu. Because mu is nabla bar closed. For the content of the symbol nabla bar differs for different letters, but you have to easily understand this. And the integral does not change. Okay. But in case of CP1 and in some other cases, but relatively rare, we can describe this pairing in another way. We represented cohomology of line bundles in Czech terms. Therefore, we have to describe the pairing in Czech terms, right? Consider H naught for positive O of k and H1 for negative, namely for dual one, sub U O of minus k minus 2. This guy is represented by a global section. And this is represented by a Czech cycle, phi, where phi is a section on U naught infinity, intersection of two charts, and is defined modular. Okay, let me continue writing heads. All right, to be coherent with the previous page. I'm caught in by my notation, as happens always. F naught minus F infinity. But if I look at what is written here, it is a product of the dual to K and canonical bundle, right? So phi naught can be understood as a holomorphic form with coefficients in a line bundle. One form. Since there was a question, I said that it is 1-0 form. With coefficients in O of minus K, okay? Then the product S times phi, S hat phi hat is a holomorphic one form with trivial coefficients, because S is in O of K and phi is in O of minus K, so they cancel, or are paired if you wish. Is a holomorphic one form on U0 infinity. Then the contour integral over the equator of these guys is the Serre pairing. Again, exercises check that this doesn't depend on the representative of this equivalence relation. Let us make a 7 minutes break. I think 10 minutes is too much for such a short lecture. So let us meet at 15:40. And you may ask questions. No questions, but still you can ask during the interval later. All right, let us continue now. This was subsection, I guess, 1.5, 1.6. Let the subsection 1.7 be deformations of holomorphic vector bundles. Okay. First, let me mention that there is a so-called modular problem, which I will not describe in any detail, but the general understanding what the problem is. How to call this brief description. Of the modular problem. Modular problem is a problem of describing deformations of vector bundles, but the main subject of this subsection will be about infinitesimal deformations. But still, let us start from finite deformations. The problem is as follows. For a manifold X, okay, for a manifold X, find the modular space of vector bundles of some topological, say, characteristic. The bundles with different Chern classes, for example, can be deformed one to another, to each other, of course. Therefore, when we speak about deformations, we always fix topological characteristics of bundles and then deform the complex holomorphic structure. Find modular space and since I'm brief, I do not mention these topological things in notation. How to describe? Let just M. M depends on X, of course, but M depends on other things. Therefore, I write simply M, which means just actually there are two types of modular space: the so-called fine modular space and coarse modular space. Let us start from the fine space. Just a second. which means a complex manifold. And a holomorphic bundle over the product of X and M, which is called universal sometimes. And the holomorphic vector bundle on M cross X such that I need notation, sorry. And holomorphic bundle E over M cross X such that M as a set is set of isomorphism classes of bundles on X, and when we restrict this universal bundle E to the fiber projection to the first factor, that is to the subset, we fix a point in M, which means an isomorphism class of bundles. Probably a better notation is like this, because E would correspond to a representative in the isomorphism class. And if restricted, it is isomorphic to E. So M is, X is the arena of for vector bundles, X, and M is the parameter space. When we vary the parameters, that is the points in M, the bundle over X changes in such a way that it belongs to the isomorphism class corresponding to a point in M. So this is called, such an M is called fine modular space. The coarse modular space is roughly the same thing without E, without universal bundle. Coarse modular space is just the structure of the complex manifold on the set of isomorphism classes. Which, as a set, equal to the set of isomorphism classes of bundles, of course. And such that for any family of bundles, such that there is a one-to-one correspondence between families families of bundles. So in the parentheses there will be a right family of bundles parameterized by a complex manifold S. So we take different families with different parameter spaces, anything we can find. And there is one-to-one correspondence between this and maps, of course, holomorphic maps from S to M. Now, exercise to check understanding is that find moduli spaces coarse. Okay, now the infinitesimal deformations are in principle, should be understood in principle as a tangent space to a point. By the space of infinitesimal deformations. Of infinitesimal deformations. This is deformations. One, in principle, should understand. One, I would say one would like to understand the tangent space to M at the point E. Deformations of E. Where E is a bundle on X, of course. But we shall define it separately from the notion of moduli space. As follows. First, First, let us start from the description of the holomorphic structure in terms of Nabla-Bar connection. So we shall give two equivalent descriptions of infinitesimal deformations. So the first is describe holomorphic structure, a holomorphic vector bundle in terms of Nabla-Bar connection, D-bar connection, sorry, D-bar connection. as I wrote at some moment, let us denote this. E is the same as smooth bundle. This curly E has nothing to do with curly E bar 4, right? Where E is C infinity bundle. Nabla bar squared to 0 is a D bar connection in E. Now, the general thing is that two different connections, two given connections differ by one form, and the D-bar connections differ by 0 one form. For nabla bar prime, two D-bar connections in E, the difference is 0 one form with values in endomorphisms of E. Is it clear what I mean by endomorphisms of E? It's a vector bundle whose fiber is endomorphism of the fiber of the original bundle. Let us consider an infinitesimal variation. If nabla bar goes to nabla bar plus delta nabla bar is an infinitesimal variation. So the above proposition showed that the space of D-bar connections is an affine space. However, the space of flat connections is some curved submanifold in this affine space because we impose the zero curvature condition. Therefore, it is more convenient to, it's easier to consider infinitesimal variation of connection because it satisfies linear equations. Is an infinitesimal variation. Then and if nabla bar squared equals 0 and nabla bar varied keeps this property, I mean, we vary in the space of flat connections, then the variation satisfies this is actually anti-commutator. But recall that the variation is actually a 0-1 form. So in terms of, if we write this guy as small a, which is a 0-1 form, on X with coefficients in the endomorphism. Then this anticommutator is nothing but the nabla bar in the joint representation applied to A equals 0. So A is nabla bar at closed 0, 1 form. What about exact forms? So the variation of the form nabla bar equals nabla bar applied adjoint applied to some epsilon, where epsilon is simply a 0 form or a section, smooth section. Those correspond to infinitesimal gauge transformations. And hence they do not change the isomorphism class. Of the holomorphic bundle E, or D-bar connection, which is described, which corresponds to it. As a result, what we get is the following. Space of infinitesimal deformations of holomorphic vector bundle E on X is the same thing as H1 of X with coefficients in endomorphisms of the holomorphic bundle, and which appeared in our consideration as Dalbo cohomology, H1 d bar X. Okay. So here, and sorry, I shouldn't. Better write here curly. Roman E, but curly script endomorphisms. Here, the Roman endomorphisms are used for global endomorphisms, not for local ones. They are reserved for those things. So endomorphisms of a holomorphic bundle is again a holomorphic bundle. Which is simply isomorphic to E star E, tensor E, and corresponds to this guy with D-bar connection. So it corresponds to the pair C infinity bundle, endomorphisms of a smooth bundle E, and nabla bar adjoint as a D-bar connection. Okay, this was item A. Now the item B. So our main result here was that this one, that the space of infinitesimal deformation is the first cohomology group of endomorphism bundle. So let us get the same thing in different way. In terms of transition functions. So for recovering U alpha, let E be given by transition functions. Modular sort of gauge transformation when phi alpha is replaced by phi alpha beta, phi beta to the minus first, something like this, for phi alpha and phi beta on U alpha, U beta. I don't write it. You should understand this already. Okay, now let us infinitesimally deform the transition functions. Is as follows. Is described by, as always, the group valued functions. It's when we have something group valued, the deformation, infinitesimal deformation is easy, is better written as in this way, that to say, it is described by such an object, okay, like everywhere, okay, like infinitesimal gauge transformations, for example, everything. So it's described by phi alpha beta to the minus first in group sense times delta phi alpha beta. Let us denote this by psi alpha beta. Now, psi alpha beta defines a one-car cycle on with coefficients in where? In the endomorphisms. It's a holomorphic function on the intersection, which takes values in the Lie algebra of this group. And the fact that it corresponds to endomorphisms will be clear when we rewrite this equivalence relation on the infinitesimal level. What is since the time is left, and in any case, I plan to give this as an exercise. So the exercise is that describe infinitesimal deformations psi alpha beta corresponding to the equivalence of transition functions, to phi alpha beta equivalent to phi alpha beta, phi beta to the minus first. And after you did this, you get that get that the same thing as above, that the space of infinitesimal deformations is H1 in Czech cohomology. Deformations of E is H1 X endomorphisms of E in Czech cohomology. And to finish this subsection, sorry for taking your time, but it's makes sense to finish here with some caution warning. So if we are given E, some vector bundle on X, and with some first cohomology group of the endomorphisms, each one of X with coefficients in endomorphism of E does not have to be the tangent space. T e to the modular space. First of all, the modular space may not exist or be unknown to exist. But even if it does exist, E may be a point of non-smooth point, or even worse, it can be excluded. In some cases, we have to exclude certain bundles, so called unstable bundles. So, but this is another subject. Probably I give example of unstable bundles on CP1, but not in more general setting. So let me finish with such a warning. Thank you.
Thank you.
Questions? No questions. All right. I mean, Kolya and myself have a feeling that some people who do not ask questions may have experienced problems with understanding of the material. If you do, please, I don't know, write something to me or Kolya, and we may organize some sort of seminar with examples or problems, collectively solving problems maybe. Be initiative in this. Okay, then goodbye.